Electrostatic charging and applications. In this lesson, we're going to review static electricity. We're going to look at charging through friction and contact, static shocks, grounding, electrostatic applications, lightning and lightning rods, and Tesla coils. And before we get started, I just want to let you know that electrostatics and static electricity are the same thing. So it's just two different ways of saying the same thing. Static electricity, review. Law of electric charges states three main things. Number one, opposites attract. So a negative and a positive will attract each other. Like charges repel. So a positive and positive or negative and negative will repel each other. They'll push away from each other. And number three, positive and negative charges attract neutral objects. So if you have a negative or a positive, it will attract to a neutral object. And lastly, static electricity is the imbalance of positive and negative charges. Atoms that lose electrons have more positive charges, protons, than negative charges, electrons. They are positively charged. So if something that loses electrons, you're going to be less negative, therefore you're going to be more positive. An atom that gains electrons has more negative than positive particles. It has a negative charge. It is more negative. One common way atoms lose electrons is through friction. When two objects are rubbed together, electrons may be transferred from one location to another. Static electricity puzzle. Using the law of electric charges, identify the charge of the objects described below. To start, draw 4 circles, then fill in the charges using the clues given. 4 spheres are suspended by insulating threads. The following observations are made. Sphere number 3 is negatively charged. Sphere 4 attracts all other spheres. Sphere 1 and 2 repel each other, and sphere 3 attracts all other spheres. So I want you to pause the video, draw the 4 circles, and then try to solve the puzzle. Okay, so here's the answer. Now the reasoning for it. Now observation 3 tells us that number 1 and 2 are the same charge, and neither one is neutral. So you know it's either going to be positive or they'd both be negative. Observation 4 tells us that number 1 and number 2 must both be positive since number 3 is negative. Therefore, not both negative, they both got to be positive. Number 3 is negative, we're told that as well. And observation 2 tells us that number 4 is neutral since it attracts both positive and negative charges. So we got that one as well. Charging objects. We'll be discussing 2 main ways an object can be charged, friction and contact. Friction. Static electricity can be produced by rubbing different substances together. This causes both substances to obtain a different charge, as one will lose electrons while the other gains. You can see that in this picture down here. So if you rub the red and the blue together, the electrons from the red move to the blue. So in this case, the red would become positively charged because it's less negative, and the blue would become negative because it's more negative. So this is seen when we rub our feet along the carpet and then touch a doorknob. The friction between your feet and the carpet creates a buildup of electrons on you. We can use an electrostatic series to determine which substance will gain electrons, become negative, and which will lose electrons, become positive, via friction. Materials higher on the series will give up their electrons to the ones below if rubbed together. So if you rub wool and foam together, the electrons will go from the wool to the foam. The foam will become negative, and the wool will become positive. Contact transfer. Contact is common and is the cause of static shocks. Contact transfer occurs when a charged object is brought into contact with, or very close to, a differently charged object. This includes neutral objects. Some or all of the electrons will transfer between the two objects in an attempt to balance the charge. So if you get a whole bunch of negative charges on your hand, and you bring your hand close enough to a metal doorknob, those electrons jump from your hand to the doorknob, and that jumping of electrons is the static shock. In the case of rubbing your feet across a carpet, friction causes electrons to be deposited on your body, giving it a negative charge. This includes your hand. When you move your hand towards an uncharged object, especially metals, the excess electrons you have transferred to that object. They're going to jump from your hand to the object that we talked about in the previous slide. The movement of the electrons can sometimes be seen as a spark and can occasionally be painful due to the speed at which the electrons transfer. Grounding. Grounding is the process of removing a charge from an object by adding or removing electrons. It's called grounding because the process involves connecting the charged object to the ground via conductor. The process is also called discharging. Now, what we just talked about your hand coming close to the doorknob and the electrons jumping, that's also a case of grounding because you're taking your buildup of electrons and you're moving it somewhere else. Eventually, that doorknob will be attached to something else, and those electrons will eventually make their way into the ground. Now, the third plug on a typical electrical outlet is the ground. It takes the excess electrical buildup that forms inside the outlet, so behind the plastic faceplate, there'll be a whole bunch of electrons that get built up just by friction or just stray electrons, and it takes them and it sends them to the ground. Grounding works because the Earth, it has so many electrons, so no matter how many more you add to it, it's still essentially a neutral object. And we can see that with this. So one Earth has approximately 6.91 times 10 to the 96 electrons. A human has approximately 2.83 times 10 to the 29 electrons. So the Earth has 10 to the 67 more electrons than a person. So it can just accept as many electrons as we can give it. Grounding examples. Static discharge can be dangerous. Therefore, precautions must be taken to reduce the buildup of electrons. So for example, fueling stations, static electricity can ignite the fuel and cause explosions. So if a big truck comes along with its big rubber wheels, those wheels touch the pavement, and that can create a lot of excess electrons on the truck. Now, when you start fueling it up, That fuel can be ignited by these electrons jumping from the truck to the fuel, potentially causing a fire. And surgeons wear protective booties so that when they're rubbing their feet along the ground as they're walking around doing the surgery, they don't get a buildup of electrons, because the anesthesia, the thing that puts you out, is very explosive, and other electrical devices and sensitive equipment that they're using can be damaged by sparks. We can also take the principles of electrostatics and use it to reduce factory waste. So smokestacks, so these guys right here, have charged areas which attract certain pollutants, so like sulfuric acid, and stop them from entering the air. Sulfuric acid is negatively charged, so the smokestack is lined with positive areas which attract the pollutant. So you see these red guys right here are going to represent our positive plates, and these blue guys down here are going to represent our negative sulfuric acid. Sulfuric acid is negatively charged, so when these negatively charged particles come up, they stick to these positive red plates, and it prevents them from escaping into the air, which is good because we don't want them going into the air, causing things like acid rain and other negative effects. So another example of electrostatics is lightning. Storm clouds form when humid, warm air rises to meet colder air masses. As these air masses churn together, lightning can be created. Lightning strikes when negative charges at the bottom of the cloud are attracted to positive charges on the ground. So we can see that here. Air currents in the storm cloud cause charge separation. The top of the cloud becomes positively charged and the bottom negatively charged. So you can see we have an overall negative charge down here and an overall positive charge up here because we're getting this swirling set of air masses. The negative charges on the bottom of the cloud create a slightly positive charge on the ground. This happens because the negative charges in the cloud repel the negative charges in the ground. So what we're going to do is we're going to push these negative charges down just a tiny, tiny bit, just so that they're not right on the surface of the ground. This creates a slightly positive top of the ground and a slightly negative part just below the ground. When the bottom of the cloud has accumulated enough negative charges, the attraction of the positive charge below causes the electrons in the bottom of the cloud to move towards the ground. This is the spark we see as lightning. It's the same kind of spark that you see when you touch a doorknob after rubbing your feet on the carpet. Now, lightning takes the path of least resistance, usually hitting the highest object in an area. Most lightning strikes are unavoidable, and therefore, many buildings, including homes, have lightning rods. Lightning strikes the CN Tower, for instance, 40 to 50 times per year, and the Empire State Building 20 to 25 times per year. Lightning rods. A lightning rod is an object that is attached to the highest part of a building and is connected to the ground. A thick, insulated copper wire connects the lightning rod to a metal plate or cable buried underneath the ground. Lightning rods allow inevitable lightning strikes to pass harmlessly into the ground and not into the building or house itself. So if you see here, and we were just to draw the path that this cable might take, it's going to be an insulated path, so a path that doesn't interact with any of the components inside the building, and it's completely separated from the actual interior of that structure. So the lightning strike can go and hit that, travel down and into the ground, and harmlessly away from the building. Check your understanding. Why is your car a good place to be during a lightning storm? So I want you to pause the video and choose option A, B, or C, and then write a short explanation, one sentence, maybe two sentences, explaining why you came to that conclusion. Now I want you to watch this video and see if your answer is either reaffirmed or if it changes as a result. Now most people say A, your tires, that they protect you, but your tires actually do nothing. It's the metal cage called a Faraday cage around you that attracts the electricity and keeps it away from you. So if this is your car, and these are your wheels here, and the black exterior of the car is metal, the lightning hits the car and actually stays along the outside of the car, and then it goes through the tires into the ground. It doesn't pass into the car, which is important because that's where you are. So if you're sitting inside the car and you're not touching anything metal, then you're going to be safe. And again, this is due to the metal exterior of the car, not the fact that you're sitting on rubber tires. Tesla coil, artificial lightning. Tesla coils can produce voltages well above 1 million volts and are discharged in the form of electrical arcs, lightning. They can create extremely powerful electric fields, so large in fact that they've been known to wirelessly light up fluorescent lights 50 feet away. So here's an example of a Tesla coil here and here. And I'd advise you to pause the video one more time and watch this video. It's pretty interesting and a pretty neat use of Tesla coils and artificial lightning. And that concludes our lesson on electrostatic charging and its applications.